Okay, so welcome everybody to the One World seminar of the International Association of Mathematical Physics. We are very honored today to have a president of the association, Kasia Rejzner, as a speaker, who will talk about renormalization of gauge theories in perturbative algebraic quantum field theory. Please go ahead.
Thank you. Thank you very much for inviting me. I really enjoy to be a participant in that seminar series, and now it's time to actually give a talk. So thank you again. Yeah, so today I want to talk about, well, the topic that has been the main theme of my career in various, guises. So it's about renormalization of gauge theories, mostly in the perturbative setting. And I'm going to tell you a bit about old things and maybe a bit about new things as well, and how these things have developed. And I assume that not everybody is familiar with the subject, so I'll really start from the very basics. All right, so let's get going. So I will start with the outline of the framework of perturbative algebraic quantum field theory. Okay, so, well, I mean, many of you probably already know what's algebraic quantum field theory. I never had to remind ourselves. So this is based on the axiomatic framework of Hagen-Kastler. So a model is defined by associating to each bounded region of Minkowski spacetime an algebra of observables that can be measured in that region. And then if you have inclusion of regions, you have the corresponding inclusion of algebras, and you obtain a net of algebra. So the theory is described in terms of giving such a net. And then, well, there are some axioms that come with it. Now, the perturbative version of that is combining, well, this basic idea of assigning algebraic structures to spacetime regions. And, well, first of all, it allows for using perturbative methods, and also it works on curved spacetimes as well as on Minkowski. All right, so here we generalize a bit. So we take a globally hyperbolic spacetime M, and then we can also, well, assign to it a space of field configurations. So that's one of the basic ingredients that we need to specify to know what theory we are talking about. And in practice, this space of configurations is the space of smooth sections of some vector bundle for M. Okay, so these could be scalars, vectors, tensors, whatever you have in the theory. And for the scalar field, this is the space of smooth functions on M, real valued. For Young-Mills, and let's start with the trivial bundle, we have one forms on M with values in some Lie algebra of a compact Lie group. And if we want to go as far as effective quantum gravity, well, then the configuration space is as follows. So again, smooth sections of second tensor power of T star M. Okay, so these are examples of things you might be interested in doing. Okay, and then dynamics, obviously this is where the whole interesting information is. So this is introduced in a modification of Lagrangian formalism. And because I want to stay fully covariant, this will be a covariant version thereof. Okay, so let me now outline first the basics of the pAQFT construction of a model, and then I will specify two gauge theories. So observables are smooth functions on the configuration space. So they're functionals on E, valued in C. For simplicity, I'm going to drop M from the notation, because from now on, let's keep the spacetime fixed. And because we want to be able to assign them to regions, the important notion is the notion of a support. So a spacetime support of a functional is defined as follows. So these are all points in M, such that if we take a neighborhood of a point and we take a field configuration psi, so there are field configurations phi and psi, such that psi is supported in that neighborhood, so that F is sensitive to that perturbation. Okay, so F of phi plus psi differs from F of phi. That's why, in a sense, a support really tells us about in what region the functional, the observable, is sensitive to perturbations. And this is a generalization of the distributional support to the situation where we have nonlinear functionals as well. In particular, local functionals are important. They're important because they describe local interactions in particle physics. And here is a definition what it means to be a local functional. So F depends on the field configuration via a finite jet at point X. So F here is a smooth function on the jet bundle. And yeah, we can also take products of such things, and then that leads to the space of multi-local functionals. So then we have also sums of products of locals. And so this space of multi-local functionals is going to be used a lot in the construction. We can also take something even more restrictive. So a functional is regular if all its derivatives, all its functional derivatives are smooth. This is in fact very restrictive because in general, this derivative, nth derivative, is distributional with some singularities. And for the purpose of this talk, because I don't want to go too much into technical details, I'm going to assume that all my functionals are polynomials, which means that at some order n, the derivatives are vanishing. So for some n above a fixed value, the derivatives vanish. Okay, so that's the setup in terms of functionals. And now let's talk about the dynamics again. So the dynamics is introduced by something we call a generalized Lagrangian. And this is a map from test functions to local functionals. Now, why am I doing it this way? Well, let me show you an example, and then maybe it becomes more clear. So this is taking your usual Lagrangian density, as you would always have it, but add to it a cutoff. So take a test function which serves as a cutoff. Why is this important? Well, in general, on the non-compact M, and we are working on non-compact M's because we assume M to be globally hyperbolic, hence non-compact. This expression, this integral over a whole manifold of Lagrangian density would not be well defined, would diverge for phi without any particularly nice follow-up conditions. So something has to, well, create a cutoff. And indeed, here we are using this test function to create like a smoothed out box where this interaction is, well, where this Lagrangian density is confined. So that's the motivation behind the definition. Here are further examples of generalized Lagrangians. So this is the one for Young-Mills, right, where we have a vector potential A, corresponding field strength, and this is the action. And then for well, effective gravity, if we want, we can use the Einstein-Hilbert action, which depends on the metric as follows. Okay, now important fact is that despite this presence of a cutoff, we can define the variation of the action in such a way that is independent of the cutoff. So although you see S here is this map from cutoffs to local functionals, there is a notion of derivative of the differential of S ds, which then is independent of these choices. And here is how it is defined. So ds at the point phi in the direction of psi is now assumed to be compactly supported, is defined by taking variation of S of f for an f which is equal to 1 on the support of psi. So here is a picture to go with it. So we have this psi compactly supported. We have f which has larger support, and in particular, this dashed line around support of psi is where f is identically equal to 1. And because S is local, this definition does not in fact depend on particular choice of f, as long as it satisfies this property. So what is this ds? Well, in fact, it is actually a one form on the configuration space. And then the equation of motion can be formulated as the condition that ds on a given phi vanishes. So this is the equation of motion. So geometrically, the solution space is the zero locus of this one form. Okay, so that's with the dynamics. And now while talking about gauge theories, we need to mention symmetries. And I should say that for this quantization of gauge symmetries, I'm going to use BV for Batalin-Wilkowinski framework. So in the first instance, I want to tell you what I mean by symmetries, and here actually more specifically local symmetries. So in a very sort of basic sense, they correspond to vector fields on the configuration space. So here is the picture. Here is the configuration space, some point phi, and vector fields are some directions there. And to be consistent with the way we chose our observables, our functionals, these vector fields are chosen to be compactly supported and multilocal. Making them compactly supported actually already restricts to local symmetries. So as vector fields do, they act on functionals as derivations. So here is a directional derivative along vector field x of a functional phi. And this is how it's defined. So we take a derivative of f and contract it with x. But we can do the same also for the action, because as I said in the last slide, we can define this Euler-Lagrange derivative as a one form on the configuration space, and we can contract this one form with a vector field and obtain a function. And here I'm sneaking in a bit of notation. So this map that takes a vector field and assigns to it this insertion of a one form, I will denote it by delta S. Okay, so now I can say what it means for a vector field to be a symmetry. So a symmetry is a direction in the configuration space in which the action is constant. So that's also the intuitive sense in which we understand symmetries. So it is a vector field in the space of nice vector fields, such that delta S of x is identically 0. So if I take the directional derivative along that vector field of the action, I get identically 0. Okay, so this is the general definition of symmetries in this framework. So that is probably not very surprising that what I'm going to try to build up is a framework for quantizing theories where these symmetries are present. And in this BV formalism, there are essentially two major ingredients. So one is how to characterize equations of motion, and the other one is how to characterize symmetries. So let's start with the equations of motion. Let's start with the dynamics. So as I said, solution space can be seen as this critical locus of, sorry, a zero locus of the one form ds. So how do we characterize it? Well, we can, at the end, characterize it as a certain quotient. And for that, we first need to identify functionals that vanish on the solution. So somehow redundant in our description. Well, you can probably figure out by looking at the previous example, right, that if I have a functional which is of this form, so ds contracted with x for any vector x, okay, that this vanishes on the space of solutions, because by definition ds of phi is 0 if phi is a solution. Okay, so clearly functionals of the form ds of x for some vector field x, they do vanish on the solution space. Now, a non-trivial statement is that all functionals that vanish on solution space are of this form. So this has to be proven. Now, luckily enough, if you're staying in the realm of local and multi-local functionals, you can show that in a large class of models, and I would say, well, I mean, all the physically relevant ones, this is the case. So it's not a very strong assumption. So with that, I can characterize the space of on-shell functionals, so functionals on the solution space, as the quotient, all functionals modulo f0. Well, I can always do that. But here is a nice characterization of that. So f0 is really the image of delta S acting on vector fields. So I can draw this little exact sequence. So there is so there is a map from vector fields to functions, and now in degree 0 we take the kernel of this map here, so all f, and then quotient it by the image of delta S, and this gives us exactly the space of on-shell functionals. But we also can add the symmetries here. So the kernel of delta S is then exactly characterized by symmetries, as I said before. So this little picture tells us everything about dynamics and symmetries. But let's talk about this piece first. So we can take, well, symmetric powers of that piece of the complex and obtain something called the Koszul complex. So this wedge thing, this denotes the exterior algebra over V, and then extend the differential accordingly. And if there are no symmetries, okay, so nothing here, then the only non-vanishing homology, that direction will be homology, is in degree 0. And as I said, it characterizes the space of on-shell functionals. And in the absence of symmetries, higher homologies vanish. And in the language of homological algebra, one says that this Koszul complex is a resolution, which is useful for some reasons. But this is not the interesting case. I mean, scalar fields are interesting, but it's not interesting from the point of view of symmetries, right? We are after situations where symmetries are present. So, but before that, there is, of course, a little subtlety with this first assumption I made, that all functionals that vanish on shell are the image for some vector field. As I said, this has been proven for a while for local functionals. taking advantage of locality and the fact that everything is effectively finite dimensional. Now, if you want to go beyond that, and in particular, if you want to go beyond polynomial functionals, then things become a bit more subtle, and they're actually way more subtle than even I expected. And this is the content of a recent paper with Eli Hawkins and Berend Visser. And Berend, who is Eli's PhD student, was very stubborn in finding all the functionality subtleties. So you can see here essentially this construction, but done for a larger class of functionals that actually we claim is the more appropriate way to perform these homological constructions. But okay, for the purpose of this talk, I'm not going to go into this. This is fun in its own right, but it's more functional analysis. Here I'm actually focusing more on the algebra. All right, so as I said, symmetries need to come into the game now. And in particular, in the context of this characterization of observables, we will have the action of some Lie algebra of symmetries, and we will be interested in invariant observables. Okay, so this is kind of general. So the space of symmetries, the way I define them, is a Lie subalgebra of the Lie algebra of all the vector fields. And obviously they have a natural action of functionals. Sort of simplifying assumption that is kind of one of the underlying assumptions of this whole framework is that this is of a particular form. So this can be written as functionals tensored, and this is an appropriate completed tensor product with some Lie algebra S, which is, well, nice enough, let's put it like this. So which is itself a space of smooth sections of some vector bundle. To see what I'm talking about, let's look at some examples again. So for Young-Mills theories, this is smooth functions on M with values in a Lie algebra of some compact Lie group. And in gravity, these are all the vector fields on our given manifold. So these are infinite dimensional spaces, but in a way they are not horribly infinite dimensional. This is somewhat under control. Okay, and now we have this action of symmetries, and now we are interested in the space of invariants, and more concretely, we are interested in functionals in observables that are gauge invariant and on shell. So invariant functions on the space of solutions to our field equations. So this is the main object we want to identify, we want to describe with our methods. And so another complex, so another piece of homological algebra that enters this is especially made for characterizing the invariants. So in fact, if you open any textbook in homological algebra, and I would definitely recommend the one by Charles Weibel, you will find that if you have an action of a Lie algebra, then it's a natural thing to take the Chevalier-Eilenberg complex to characterize the invariants. So this is its underlying algebra. So you take the exterior algebra over the dual of your Lie algebra and tensored with the space of functionals where all of this is acting. And then the differential encodes the way these symmetries act. So in the zeroth order, you have just F, so just functions. In the first order, you have forms on the Lie algebra valued in functions, and this is defined as follows. So your form, it eats psi, which is an element of your Lie algebra, and then spits out how psi is acting on F. So, and we know how acts, it acts via directional derivative along the appropriate vector field. And then you can easily see that, well, the kernel of this map will characterize invariant functionals. So functionals for which this vanishes for all psi in S. And this is why, again, we have a nice characterization. H0 of gamma characterizes symmetry invariant functionals. So we have these two pieces. So we have the dynamics, which is characterized by the Koszul complex, and we have the invariance under symmetries, which is characterized by Chevalier-Eilenberg. This is all very classical still, so nothing quantum yet, but this is setting the stage for a nice description of these ingredients so that it's well, easier to quantize. All right, so now we combine these two pieces together, and this is where something known as the BV complex appears. So first of all, we want to construct its underlying algebra. Let me go back 2 steps just to show you the motivation behind it. So for the Koszul complex, we took exterior algebra over V. Geometrically, this is the space of multi-vector fields on your configuration space. Now, then for the Chevalier-Eilenberg, this underlying algebra is actually something like a space of functions, but it's a space of functions on a graded manifold, where apart from this original space of configurations, we add S, so the gauge algebra, but we added in shifted degree. So let me see if I can still annotate things. So this space can actually be seen as, say, oops. I don't know if I can still do this. No. I can still do this. Okay, so this is the space of multi-local functions on your original configuration space plus this S, but then shifted in degree 1. Okay. So with appropriate meaning of what that should be. Okay, and then if we follow this idea we had before, that we should take, in fact, multi-local vector fields on that. Sorry, I think I hear a bit of echo, so maybe people should mute themselves. Okay, thank you. Then we should, in fact, be taking multi-vector fields on this new space. Okay. I think this is working. All right. So back to the plot. So in BV complex, we take this extended configuration space, which is E plus S in B. And then we take the space of multi-vector fields on that, which, again, in the language of shifted geometry, is the odd cotangent bundle on this space, but maybe this is just for the connoisseurs. All right. Okay, half time. So this is the underlying algebra, and we also need the differential. And here there is some simple way of doing it. So we start with taking the sum of the Koszul, Tate, and gamma, and the Chevalier-Eilenberg differential. And then we have to see if did that actually define, if this defines a differential. So in general, we might have to add some further terms to that. But in simple cases like Young-Mills or even effective gravity in metric formulation, this is enough. So this is all we need. This is the BV differential. We can go ahead and use it. And then the fun fact is that, this construction gives us not only a characterization of F as invariant, so the gauge invariant on-shell functionals, as a cohomology of the differential, but you can also nicely break it down and understand it as taking the cohomology of gamma on the homology of delta. So these two pieces going on shell and then taking invariance are explained by these two steps of taking cohomology. And then this is kind of sort of bunched together in this BV differential, which is the sum thereof. So the only thing you need to know if you want to go ahead and work with this space, you need to take this BV complex and then take the zero cohomology. So the strategy I'm going to use now for quantization is to quantize this larger structure, so this extended thing, this BV complex, together with this differential. It also has to be quantized. And then remember that the physical information, namely gauge invariant on-shell observables, are encoded in the cohomology of the differential. Okay, so that's the take-home message. Before we go there, there's one more structure I want to introduce. So there is some nice Poisson, or rather shifted Poisson, graded Poisson bracket. And in fact, it's actually related to a Schouten bracket on multivector fields. Maybe I should remind people what's a Schouten bracket. So forgetting about like all these extra fields and shifting and whatever. So the Schouten bracket is something which is defined on multivector fields, and then if you take a bracket of a vector field and a function, this is defined as the directional derivative. Okay, so this tells you what's the bracket between degree 1 and degree 0 things. If you take two vector fields, this is so 2 degree 1 things. This is just a commutator. Okay, and then for further degrees, you use the graded Leibniz rule. Okay, so that is the Schouten bracket on the space of multivector fields. And now you have to remember your gradings. This also works on this extended configuration space. So also works for multivector fields on this one. Okay. Now, what do we use it for? So we can show that the differential, even though it's not inner with respect to this bracket, is almost as good as inner. And again, we use this trick with choosing a test function to be equal to 1 on a particular region. So I can write delta S of x for a vector field as a bracket with S of f with our action, as long as f is chosen to be identically 0 on the support. And then, okay, so then if we want to also include, sorry, maybe I did Okay, right. So this is just the delta S. Now, if we want to include also gamma, so if we want to write the full BV differential in terms of the bracket, this is also possible, but we have to modify the action. So this is this whole story of adding anti-fields, ghosts, and all this extra stuff to your interaction Lagrangian. You build this extended action, and then you can implement your BV differential again as bracketing with the action. This is getting a bit technical, so I'm going to maybe stop here with the level of technicality. But the sort of important point about it is that now the condition that this BV differential is nilpotent, so S squared equals 0, this actually can be written in terms of a condition for this extended action, namely that the bracket of the action with itself is, well, it could be 0. 0 is not bad, but actually in this context is enough that it's equivalent to 0 in the sense of equivalence where you identify Lagrangians which differ by a total divergence. So to understand that, note that we have here this condition with choosing f so that f is equal 1 on the support of the argument. So we can essentially identify things which are supported only on the support of df, okay? Because that, in the region where our argument is supported would be 0, right? Because in that region, f is 1. So this condition here is then called the classical master equation. And well, it encodes the fact that our differential is in fact nilpotent. Okay, so now we are ready to quantize things. So in the rest of my talk, I'm going to quantize. Let's see how well we go with time. So the basic thing I want to talk about is BV, but later on, I want to also include what happens on the boundary. So this is called BV, BFV. But let's take things slowly. So now I take my extended action. I added whatever fields are needed there. And now I want to quantize it. So this is very similar to what I would have done for a scalar field, only with maybe some extra degrees of freedom. But the idea is always the same. So you linearize around some configuration so that you have the quadratic piece and the interaction, and then this quadratic piece will contain fields and these various extras. And then, so the anti-fields are essentially coming from the vector field. So think about, having vector fields as, maybe I should also write this down. I could write vector fields in a slightly formal way as some coefficient times derivative. Okay, and formally we can think of these as generators for the fiber, so generators for the space of multivector fields, and these guys are called anti-fields. So when you write down your expression of the extended action, you will have those around. And in particular, for the quadratic piece, you can expand it in something which doesn't contain those anti-fields, just the usual, and the rest. Okay. And this S00, so the piece of quadratic action which doesn't contain anti-fields, we can take the derivative thereof and obtain the equations of motion operator. So this is the operator which gives us the linearized equations of motion. And then we assume that our construction of this extended action with all the extra fields was performed in such a way that P is a normally hyperbolic operator. This means that somewhere along the way, we must have done some sort of rearrangement of things to ensure that this is the case. But again, I'm going to leave it for you to read about in papers, and just focus on the basic structure. So let's assume that somebody gave us this S extended such that this lowest order piece after linearization gives normally hyperbolic equations. If this is the case, then we can just go ahead, the usual prescription for quantization, exactly the way we would have done it for a scalar field. We note the existence of retarded and advanced green functions because we are on a globally hyperbolic manifold. And then we define the Pauli-Jordan, namely the commutator function, which is their difference. And then, okay, so here's yet another Poisson structure. What I introduced before was a shifted Poisson bracket. Now, we also have the regular Poisson bracket, which corresponds to the canonical bracket of the theory. And this is given by taking, for two observables, we take their variations and then contract it with this Pauli-Jordan function. And again, as in the scalar field theory, this essentially tells us everything we need to know about the canonical structure. And then in order to get free quantum theory, we quantize it. The way well, there are many ways to quantize things. The preferred way for me in this context is to use deformation quantization. So I define a star product, which is now a formal power series in H bar. At this point, this is more of a choice. Maybe, yeah, I guess I shouldn't say formal power series because F and G are a polynomial. So this is actually an honest, to goodness, even finite power series in H bar. But yeah, for convenience, I think I want to think about H bar as a formal parameter because very soon we will be in the situation where we are actually talking about formal power series. But obviously for free theory, yeah, everything's finite. And this W here that I used is a 2-point function of a chosen Hadamard state. So on Minkowski, we have the Weizmann 2-point function. On curved spacetimes, we have more states. We have actually a big class of interesting states, which is that of Hadamard states, which are characterized by the singularity structure of their 2-point function. So W, this 2-point function, has delta as the antisymmetric part, right? So that it gives the correct commutator, and it has this extra piece, symmetric piece, H, which then the choice of H corresponds to the choice of a Hadamard state. And in general, there is no way to distinguish one on a generic spacetime. Okay, so with that, we actually have quantized the free theory. Okay, we have the star product, we have the star operation, which is just given by the complex conjugation, and we are done. So what's next? Next, we want to actually get the interaction back into the game. And in the first pass, let's look now at these very, very regular, nicely behaving observables who have smooth derivatives. The reason I'm starting this way is because they're very tame in terms of singularities, namely they don't have any. So that avoids some of the problems that we're going to encounter later. So for those, I can directly define something I call time ordering. So first of all, very similar to the definition of this 2-point function, we can introduce the Feynman propagator somehow associated to that 2-point function, which looks almost exactly the same, only the sign between delta retarded and advanced is not minus but plus. Okay, and h is the same. And then this thing just takes derivatives for an observable and contracts it with the powers of the Feynman propagator. This is very similar to what one does in, say, traditional perturbative QFT. And in fact, you can think of this t as taking the path integral of f with a Gaussian measure with covariance given by this Feynman propagator. This is a bit formal. It would be well, precise if we were in Euclidean signature and well, preferably in finitely many dimensions. In Lorentzian, this is more of an intuition. But the important thing is that this t essentially contains the same combinatorics as the path integral. So instead of doing the path integral as an integral, we can just work with this t in terms of practical calculations. And then we define the time-ordered product here on this. Now let's go to formal power series on this space of regular functionals formal power series by twisting the pointwise product of observables of functionals we had before using this t. Now, why is it called time-ordered? So a basic reason, okay, a basic motivation for this definition is that if the supports of arguments are ordered in time, so the support of f comes later than the support of g, then these coincide. And I guess I should say, if it's the other way around, then the order is changed. So if the support of g is later than the support of f, then the order would change. So here, if we have, oops, that is not what I was intending to do. Oh yeah, this, okay. Yeah, I don't know how this works. Sorry, I went absolutely out of practice in terms of these Zoom talks. Oh, all right. So, yeah, so what I wanted to say is that if the support of G is not later than the support of F, then F time ordered G is G star F. Okay, so the order is switched. Okay, splendid. So now let's put back the interaction in the game, as I said, and this is done using what's called the formal S matrix. It is removed a couple of steps from the actual S matrix. The first thing is that this V here, remember the cutoff function we introduced for all our Lagrangians. So this V is an interaction with a cutoff. So first of all, if we wanted to talk about an actual honest to goodness S matrix, we would have to take the limit of that cutoff going to 1, which is the adiabatic limit. But in fact, for the construction of the local algebra of observables, we are just happy and good enough with this formal S matrix. And this is easy to define actually with all the machinery we have right now. So this is the time exponential of the interaction. And then the interacting fields, this is also coming out very nicely. We take a relative S matrix. So this is this product here, and take the first order of that in F. This is usually called the Müller map, and this gives us the interacting field corresponding to F. And again, I'm working with these regular functionals, so for now completely discarding a sort of singularities. And then I can define also the interacting star product, which has the whole knowledge of the interacting theory by deforming the original star product with this map. So this map can be thought of as relating free and interacting theory. All right, so but of course this is not the end of the story. So if I want to do an actual well, I mean, physically motivated theory, let's say, then V should be local. So local functionals that are higher than linear are not regular, because in derivatives you would get the delta distribution, which definitely is not smooth. So the renormalization problem can be formulated as extending this this product, this time-ordered product, to V's that are local and nonlinear. So that's what renormalization does for us. So I'm not going to go now into this whole renormalization issue, because this is a separate talk. So the renormalization prescription we are using is the Epstein-Glaser renormalization. This is a topic in its own right. The important thing is that it does deliver us now a version of this product, which is actually well defined on multi-local functionals. So that's the important bit. So you put things into that black box, and then you get the right sort of product. So now let's come back to gauge theories. And well, I mean, up to now I could have been talking about the scalar field, and you wouldn't see a difference. But no, this is more specific to actually talking about gauge theories. So the way we linearize our theory, we also linearize the BV operator. And now there's an important condition for our compatibility between the interaction we introduce and this linearized BV operator, namely that this formal S matrix is invariant under this linearized BV operator. And this condition corresponds to the quantum master equation. For regular functionals, I can actually compute things explicitly, and I find out that this bracket with a 0 can be written in the following form, where you might recognize that this first piece is actually what entered the classical master equation, but there's a quantum correction with this funny operator which looks like Laplacian, but now you have a derivative with respect to the field, and this is the derivative with respect to the anti-field. Okay, so this is what comes out of the computation. The problem is, again, you know, there are singularities, and naively, this applied to a local vector field would be divergent. This would be very, very badly behaved. So what's the way out? The way out is that in this whole construction, we actually should use, instead of this naive T on regular functionals, we should replace that with renormalized T, okay? And then everything will work out nicely. All right, so the standard form of quantum master equation that you can see in other approaches as well is this one, but if you do the proper renormalization, then this actually is replaced with renormalized version of delta. But this comes out naturally if you replace this with the renormalized product. Oh, I cannot write on this anymore. Okay, so this has to be replaced with the renormalized product. Okay, I'm running slowly out of time, so I'm going to conclude this and then give just a very quick remark about the BFV case. Okay, so yeah, so that was the condition for the S matrix, and now let's talk about the deformation of the operator. So we should also, as we deformed the products, we should also deform the BV operator. So if we deform a 0 using this time ordering map, then we get the classical piece plus correction with this operator delta. So that's the free theory. And for the interacting, you should be deforming with RV. And this, okay, I mean, this is what it is. This is the definition. But it's not, in general, it wouldn't be something particularly nice. And what's kind of disturbing, it might not be local. So RV is not a very local map. So this this operator here might not be local. Okay, in a certain scenarios, it is local. And well, we want to use it to compute homology and get quantum gauge invariant observables. So for practical purposes, but also conceptually, it would be nice to ensure that this is in fact local. But this is the case if we assume quantum master equation, then this simplifies significantly, and we get a piece which is the classical BV operator plus the quantum correction. So quantum master equation guarantees that this operator is in fact local and given in a nice form. And again, this delta here gets automatically renormalized if we are using the correct time-ordered products. Okay, but even before that, even if we stick with regular functionals and just work out the algebra, there is certain well, sort of gratifying that you can get the same result as one gets in the path integral, but without actually doing path integrals. And then upon applying the Epstein-Glaser renormalization, this gets the nice renormalized version. So this is the last step, which I'm not going to perform explicitly, but the whole algebra is the same. You just replace this product with the renormalized time-ordered product. Okay, so let me conclude. So this concludes the sort of basic BV quantization, and I wanted to just say a few words about what happens in the presence of boundaries. So this is more the focus of the current research on this topic. So yeah, so in a sense, one can summarize these structures I mentioned here as assigning to the bulk of the manifold some well, shifted symplectic structure. So that was this BV bracket, and some vector field that Q that gives us this BV differential. So these are these pieces, and extended action functional, which in the absence of boundary is related to this odd vector field, so to this operator via the symplectic structure. Sorry, shifted symplectic structure. So these are the, well, this is a sort of graded geometry way of putting together all the pieces we have seen before. But in the presence of boundary, well, first of all, you will have the corresponding structures living on the boundary, but, well, I mean, with appropriate grade shift. But then some of the properties you would normally expect in this BV setting that we have used before. So for example, as I said, the relationship between the BV differential and the action and the anti-bracket, these fail, and they fail modulo things that live on the boundary. So there is a whole hierarchy of identities, relations between these structures. So let me just comment on the first two. So here, this says I am running out of time, obviously. So the first one says that the variation of the action is given in terms of the symplectic. Yeah. So there are the two identities. So the first identity corresponds to the fact that the BV differential is given in terms of the bracket with the action. And as you can see in the situation with boundary, it can fail, and it fails modulo a form, a symplectic form, which is supported on the boundary. And the second of these corresponds to the nilpotency of the BV differential. And here, I told you before that in the usual case without boundary, that fact was described by the classical master equation, so by the statement that the bracket of the action with itself vanishes. And here, this bracket might not vanish. It again vanishes modulo something that lives on the boundary. This S boundary is actually the corresponding boundary action. So these first two identities correspond to the failure of some of the facts we used, first in classical and then in quantum theory for the bulk. So now this whole formalism I was talking about has to be modified by adding the possibility that both the classical and the quantum master equation fail modulo some boundary terms. Okay, and then you can take the next level. So if you have the boundary of the boundary, so if you have corners, then again, various identities on the boundary can also fail up to these corner terms. So the current research is in trying to understand how to quantize it using the similar methods on the boundary. And an interesting application of that is the situation where we have asymptotic boundary. So let's say we start with something which doesn't have a boundary, like Minkowski spacetime, then we compactify it and then sort of add the boundary. So if you think about the conformal diagram for Minkowski, then Scry is the boundary. And then one can also apply similar methods to understand the relationships between the bulk fields and sort of asymptotic fields on Scry. Okay, that's what I wanted to say. Thank you very much for your attention.
Thank you very much for this beautiful talk, Kasia. Are there some questions or remarks?
In the meantime, I might be able to get my computer back.
Yeah, so if anybody has questions, I suppose you just unmute yourself and ask. Okay.
I have a couple of questions,
Yeah,
perhaps
go ahead.
naive ones. So please forgive my naivete. But the first one regards the time ordering used in the construction of the algebras.
Yes.
In conventional Minkowski spacetime quantum field theory, there's this argument based off of Lorentz covariance that the time ordering doesn't affect that your choice of time ordering doesn't affect the theory that you construct. Is there a similar argument in this framework for arbitrary curved spacetimes?
When you say it doesn't affect the theory you construct, what do you mean by that?
Like if you use any foliation, any of the flat foliations of Minkowski spacetime as your time ordering, I think the statement is that Lorentz covariance, once you prove Lorentz invariance, you have that all correlation functions are Lorentz invariant. So it doesn't matter which time ordering you would use to begin with.
Oh, okay, right. So here there is something called the general local covariance. So the statement is that this time ordering can be performed. Actually, it should be performed in a locally covariant way. So that it kind of restricts the freedom of the choices of time orderings. But yeah, I mean, on curved spacetime, you require that general local covariance, and you can show that indeed you can construct time-ordered products and this works. So I think this is the analog of the statement you have.
Okay, I see. Thank you. Okay, my My other question was about the connection of the renormalization procedure to this thing by Hollins and Wald about the operator
Oh,
product
yes,
expansion.
yes.
Is there a way to read off those short distance singularities in this perturbative framework?
So you mean the operator product expansion or what?
Yes.
But you said so because right, I mean there is the paper of Hollands about renormalization of Young-Mills theories, which is then exactly using the framework. Well, it's the predecessor of the framework I was talking about. So the paper of Hollands from 2007 essentially like completely solves the problem of construction of time-ordered products in Young-Mills. And then you can use it to sort of frame it in terms of OPEs, as is done later, but you can also phrase it in this BV framework, as I've done a couple of years later. So it is equivalent.
Okay.
Okay,
thank you.
I will try to perform the switch to my laptop again. Let's see if it works.
Okay.
Okay.
Welcome back. Okay. So
Spectacular success.
very good. Any other questions?
I have one final question.
Go ahead.
Yes.
Which regards the presence of gauge fixing conditions in this construction. I suppose that if you just do a reduction for a standard quantum field theory, gauge quantum field theory, you don't maybe in the BV BRC you don't have to worry about this so much, but for effective gravity in particular, it seems like the construction of the algebras of the algebra associated with the region should depend very much on the gauge fixing conditions that you use to define it. So is there a way to put that into this?
Yeah, so okay, yeah, you're right. So for the for gauge theories, maybe it's not that relevant. So let's see. The BV framework essentially guarantees independence of the algebraic structure of the gauge fixing condition. So theories constructed for different gauge fixings would lead to different BV differentials, but the corresponding BV complexes would be quasi-isomorphic. So that's for ordinary gauge theories. Now, in gravity, there is an extra level of complication, namely the gauge invariant observables have to be constructed in relational way. So there is an extra layer of choice. So you typically would, I mean, I would typically use relational observables, which kind of rely on the choice of coordinates constructed from the metric and dynamical fields. And that choice, then things depend on that choice. So that I think then that's compatible with what you're saying. And then of course localization also depends on that choice, because that's essentially choosing your local coordinates.
So is there a specific point in this construction that you would put that that information in?
Yeah, I mean, actually, that's probably the point I didn't tell you about. But so here I would very naively assign observables to regions by assigning functionals of a given support to a region. And then for gravity, where you're talking about relational observables, that step would be different. So then I would have to refer to a particular choice of like a reference frame in terms of these dynamical coordinates.
Okay, thank you.
Thank you.
Okay, any other questions?
Yeah, can I ask a very naive question?
Yes,
So
yes.
I understand this is a perturbative approach and you're not discussing about convergence or anything. Is that
Not
correct?
today.
Okay, not today. Yeah. That's a question. So what are you going to talk about tomorrow? So what is the ultimate goal of this kind of perturbative algebraic quantum field theory approach? So are you one day going to prove the convergence and go to the sort of construction of gauge field theory? Is that the goal, or?
Well, I mean, there are various goals. I mean, in terms of non-perturbative results, where there was a talk of Klaus before in this seminar about this idea by Klaus and Detlef Buchholz on well, essentially framing some of these algebraic structures in terms of sister algebras. So you have this dynamical sister algebra, which was first proposed for the scalar field, and then there were a few later results, in particular one which incorporated global gauge symmetries in the version of the Noether theorem. And currently we're actually working on incorporating gauge theories into that framework. So I would say that this is, not just because we are working on it right now, Klaus probably hears me, but I think this is a natural next step to package it in terms of the sister algebraic framework. And the other thing is that the asymptotic story and using these things with boundary. I mean, this is going sort of slightly different direction than non-perturbative results. It's, yeah, but sometimes you can say more about asymptotic theory than you can say about the bulk theory because it might be more tractable.
Okay.
But yeah, I don't want to make any crazy conjectures here because it's recorded.
Yeah, thanks. Thank you.
Okay, any other questions? Then maybe let me ask a question following up on what you just said about this recent work. Maybe you could comment a bit more on infrared problems, on this asymptotic
My favorite.
symmetries.
Okay, here is a secret slide. Yeah, so that has in fact been applied. At least the classical structure. So there is a paper from already 3 years ago with Michele Schiavina where we used this BFV framework to talk about asymptotic QED. So trying to understand some of the statements by Strominger and the earlier work of Andrzej Herdegen in this setting. And we are in the process of quantizing it. So this is the picture with Scry. So yeah, what we have done was to analyze this sort of BFV structure. So you have the usual, well, we did it for scalar QED, but you have the usual scalar QED in the bulk, and then you have the asymptotic theory on Scry, and then you find out, for example, that your large gauge transformations are not the symmetries of this Scry, and as one kind of expects in this BFV setting, this failure to be symmetries is characterized by things that live in the corner. But yeah, so that was purely classical analysis, but we are now hard at work to make it quantum. So
Okay,
hopefully
I see.
But yeah, I mean, in terms of infrared problem, let's see. So I mean, I think there are several ways to think about it. I mean, the question is, how do you want to see this structure on Scry? So, well, in the approach proposed by Andrzej Herdegen, one also quantizes these degrees of freedom at infinity, this asymptotic structure. So one obtains a theory which has non-trivial role of these quantum boundary observable. So it's non-local. It's not a traditional AQFT. So and that addresses the infrared problem, but you kind of have to go beyond locality. So I guess one of the things I'm trying to do with this BV-BFV setting is to also have a formulation which is slightly non-local. So the construction I presented before with only the bulk, you essentially construct a local net of algebras. And going beyond locality, so towards trying to solve the infrared problem in that way, you break the locality a bit, but in a controlled fashion. So including those boundary and corner data. But yeah, so that's the work.
Okay, thank you. So any other questions? If not, then maybe let's thank the speaker again and stop the recording and move on to the informal session. So thanks a lot for this nice talk.
Thank you.